given by Professor Huang-Hsiung, who is the director for the CCliCS. And he will give an overall progress report for this project has been done for the last 3.5 years. Let's welcome Professor Xu.
Good morning. I have to thank the Ming-Hui and Wei-Ting Chen and Xu and a bunch of young scientists who volunteered, actually, perhaps I should say, were volunteered to organize this workshop in different ways. They tried to encourage more discussion. So I guess the agenda or the way of this workshop where we carry out is slightly different from the previous two. Okay, so I see many old friends here and some new friends. So this thing I have to do every time, like to update you our recent progress of this so-called CCliCS project. It's called Consortium for Climate Change Study. Okay. So especially, actually, this project not just involves the modeling, it also includes some diagnostic work. But today I'm going to mainly focus on climate modeling activity in this Consortium for Climate Change Studies. And this project actually consists of 4 sub-projects, and the PS name are listed here. Myself and J.P. Chen, Patty Lin from NCU, and J.P. Chen from National Taiwan University, and Chen-Ta Chen from National Taiwan Normal University. Actually, he's now is in Yangzhou, so he cannot be here. So I will present his talk for him tomorrow. Okay. So as I say that we have 4 projects here, and the first one is called Laboratory for Climate Change Research, and the second one led by J.P. Chen is development of cloud and aerosol precipitation for climate models, and the sub-project 2 is development of regional climate modeling system, and sub-project 3 is quite challenging, is detection and attribution of the impact of anthropogenic greenhouse gas emission and warming on the change of climate weather systems. Okay. So this project began in 2011 and will end in July 2016. So we are now in our 3.5 years. So we have 1.5 years to go. Okay. So this, and we are hoping that academician Liu just asked me what will happen to us after the end of this project. So what we will do is we'll try to have a second phase of this project. Okay. After all, for climate modeling of such a complicated system, it's 5 years too short. Okay. So hopefully we can have another 5 years extension. Okay, so I will be going through my PowerPoint very quickly, just to give you a brief flavor of the project and about what we have been doing in the past 3 years. Okay, so this is the research team member involved in the first project, Laboratory for Climate Change Research. So within this this project, we working on 2 models. The first one is CSM, and the second one is HIRAM. So CSM collaborate with NCAP people. So we try to make change to some physical parameterization scheme in the CSM. So try to make it our own models. Okay. So these are the thing we have been working on, and the member of for each teams, and also work closely with SJLIN in GFDL. So we use HiRAM to do simulation and also help to develop HiRAM. And another part is about the climate diagnostics. Okay, so this is a list of very complicated things we have been doing. So it involves the convection and PVL schemes, a cloud fashion scheme, radiative transport scheme, and topographic effect on solar radiation, and warm cloud microphysics in convection, aerosol, and also something on gravity wave drag. And for land model part, we try to incorporate the irrigation mechanism in the model and try to improve the representation of groundwaters. And also 3 professors working on the ocean model from different perspectives. And we're hoping HOE will ask, that's our mission, to have something like a new ESM for Taiwan. It's a global model, right? Okay. So we may call it a Thai ESM, and that we will schedule to deliver a so-called beta version, probably not a complete version, the beta version of Thai ESM by July 2016. And it's very likely this scheme will be incorporated in this revised CSM. And other schemes, we will see how much progress we will make, and then decide where to include that in the models or not. So I will give you some quick description of some work we have been doing. For example, the first thing is going back here, we replaced this convention scheme and PBL scheme in the Camp 5 by the NCEP GFS physical packages. So after we're doing that, we do see some improvement. But I guess that in the afternoon of tomorrow, you will see some bad parts about this model when we incorporate this new scheme. Not a bad part, but it's something need to be improved. Okay, so something here is try to look at this the distribution or convection from of the coast of California to the tropic. So supposedly you're supposed to see this elevation of the cloud from this subtropical part to the tropic. So it should be like this. But in the Camp 5, this sort of feature cannot be simulated in present model. So after we incorporate this scheme, it does simulate some feature that looks more realistic. Okay. I guess you will see more detail of this either in the breakout session or in our posters. And also, with the help of the CMR, we use this technique of transpose emiss experiment. So I try to test the GFS scheme in the Camp 5. So I would do, so Ichiwan and others did a series of simulation, and it does show that up to implementing this new scheme, it enhanced the simulation of this extreme rainfall. Okay, it's much closer to the trim. And also it has some improvement on in the diurnal cycle. Again, this is work done by Ichiwan. So here is the trim observation. So this is the rainfall diurnal cycle. And this original Zhang Bafaran scheme in Camp 5. And here she actually already did one thing, is implementing this triggering function of SAS into the Zhang Bafaran scheme. Okay, not completely replaced, but just including this triggering function that. even by just doing that, you can improve the simulation of diurnal cycle. So this the modified Zhang-Ma-Fahren scheme. And okay, it's a very complicated picture, but look at this. So you see this, the convection will propagate in a days. So, but Zhang-Ma-Fahren scheme cannot do that. And after you do that, it's not exactly the same as the observation, but we do see some improvement. And this another picture of that is you see using the trim observation, you see some propagation here through time. Zhang-Ma-Fahren does not show that. After you change this sequence scheme, you start to see some propagation, although it's still too weak. And if you look at take a look at this Borneo Island, you see this propagation at this time and outward, okay? And Zhang-Ma-Fahren scheme cannot do that, but after you change the trigger scheme, and it does show some propagation, okay? Although it seems to be scale too broad and probably too strong. And Faru Pan actually proposed a new cloud fraction parameterization scheme. So I just tried to replace a very simple-minded way of deciding whether you have a cloud or not by so-called humidity critical number, okay, like a 0.8 or 0.89, that sort of thing. So he used it derived the equation, and so then we implement the equation into the model. So now we are doing the testing. Okay, and also Mingda Zhou is working with us. He was working in NASA. I guess some of you know that. And so he's interested to see, to compare his radiation scheme, correct, with RTMG. So this some comparison between two schemes. They are very different schemes. So because RTMG now is a very popular scheme and it has been used in many models, but we just try to see to make a comparison. And by doing this, we actually our people learn a lot from about these radiation schemes. Okay. So this a simple comparison with the line-by-line calculation of Hytron based on 1996 and 2012 data. And here is a vertical. This was done by a 1D model. Okay, so the RTM and the QREC does not show much difference in the low atmosphere, but it starts to see some significant difference in the lower stratosphere. Okay, so you see the QREC seems to be closer to the line-by-line calculation. Okay, so potentially it is potentially important if one want to move up your top of the model to a higher atmosphere. Then you need some more accurate calculation of radiations. And I guess some of you have seen this a couple of times. Also, William Li tried to incorporate the topographic effect on solar radiation into the WRF and the CSM. Okay, so by using a very complicated model based on the photon detailed calculation, so you can see how much solar radiation was actually absorbed near the very complex 3D topography because of the reflection back and forth. So, and he showed that the difference in solar radiation can be as large, this is for Tibetan Plateau area, can be, I mean, the plus and minus can be as large as more than 30 watts. So that's a huge number. So he has and it also has some impact on total cloud fraction, precipitation, and especially importantly on the surface hydrology. This is an example of surface snow covers. Okay, so actually I did not show it here. After incorporating this scheme, it also had influence on this large-scale monsoon circulation, not just locally. Okay. Because you change the diabatic heating near the Tibetan Plateau, it's going to excite different kind of stationary wave. Okay, and also one of our postdoc, Zuling Lai, she has been working with the NCAR scientists by adding this gravity wave track or revising the gravity wave track, including the not just a dip convection, also shear convection, also frontal activity. Okay, so to include those gravity wave track effect into the model and try to see, and also by increasing the vertical resolution, and to see its impact on QBO. So they have shown that up to you, especially by increasing the vertical resolution, CAM5 can realistically simulate a QBO. Okay. And here she actually did a comparison. Okay, so here is when they only include this gravity wave track from deep convection. And the QBO, you see some QBO feature here, but the period become too long, unrealistically long. So after adding this gravity wave track induced by the shear convection, and they got the shorter periods or a period closer to observations. So, and Ming-Fei Rou working on lens surface process or making change to CLM. So I guess here I show two parts of his work. The first one is in the CLM, in the CAM5 now, you use the parameterization, the constant parameterization for every point in the model. But he tried to get the ultimate parameters by diagnosing the data from grass and the stream flow, also to make a variable in space. Okay. Another thing is quite interesting. He has been doing some study on this potential impact of wintertime water management, basically the irrigation over Asian low latitude. So this is just one figure he showed here. So after incorporating irrigation in this area, so it cooled the surface temperature, but surprisingly, actually, it has also made the North America warmer. Okay. So exactly how that works, I guess it will need some diagnostic work to understand. But again, it just shows that if we change something locally and then we change the heating distribution, and the impact or influence could be global. And then we have three professors working on ocean model. So this work has been done by Professor Zhang Yuheng. Actually, he was a professor at National Taiwan University, but he moved to NCAR a couple of years ago. But he's still collaborating with us closely. And so he supervised one postdoc and one research assistant here. So what they do is he actually ocean model called TeamCom. So he's coupling the TeamCom to CS1. So basically they have complete the coupling, the coupling coding work, okay, and do some testing run, long-term testing run. So they have been used code 2 forcing to drive the ocean model. And so they have been doing the simulation for, I guess, more than 100 years, and they are continuing doing that. And the model seems to reach some sort of stationary or equilibrium by year 60 or 80s. Okay, so they also demonstrate that by adding the surface wave-induced mixing and by adjusting the vertical mixing, they were able to reduce this original bias like this, like a 9 degrees C to 3 degrees C. Okay. And Professor Charong Wu at National Taiwan Normal University, they also try to work on this the surface wave-induced vertical mixing in the CSM1. So after they incorporate that into the model, and they see some, they have improved the simulation of Khotan a little bit. And later on, they will try to make the effect feedback to atmosphere model. And another work, probably relatively simple, is the by coupling a very high resolution, I mean the vertical high vertical resolution of slab ocean model, okay, TKE model, called SIT, developed by Ben Zhuang, professor at Zhongxing University. They couple that to CAM5. Why we do that? Because previously, when they couple this SIT to the ACAM5, and they found the great improvement, significant improvement in MGO simulation. Okay, for example, this observation and this ACAM5. So originally, ACAM5 simulation is not particularly good, so it produced a relatively realistic spectrum. So we try to do the same thing by coupling this SIT to CAM5 to see whether it works in other models, and also by coupling to another model called HIRAM. Okay. Actually, so this is what the preliminary result we got. This was the original result from the CAM5 before we coupling SIT. So it does simulate some MGO, but it's not as strong or as good as the observation. So after coupling SIT, the preliminary results show that they actually some improvement. Okay, and the performance is not worse than CAM5 coupling to PAP2. Okay, probably even slightly better. Okay, but if you couple that to an ordinary slab ocean, and the improvement is not significant. Okay, and this improvement is especially significant or notable during the summer season. Okay, when the simulation using a CAM5 control or coupled to a slab ocean or coupled to PAP2 cannot simulate the signal or intrasignal oscillation or meta-enduring oscillation correctly. But by coupling this SIT, it does do some good work. And so that's something about the CSM1 or the future Thai ESM. And another thing is we use a HIRAM to do a very high resolution global simulation for present climate and the future climate. Okay, so so this is the two time-slide experiment we have complete. Okay, for the future projection, that's for RCP 8.5. Okay, so we just produce this data to understand the future climate change or impact on this on weather and on climate, and we provide data to another project. They use this data to do some dynamic downscaling to Taiwan to provide the information on climate change impact on Taiwan at the end of the 21st century. So this just show you that HIRAM basically simulate realistically the rainfall distribution in a global scale or in a monsoon scale. and it actually enhance the strength of extreme rainfall, closer to trim or even stronger than trim. But there's also some problem is this high rain model produce too much and too weak, too many weak tropical cyclone in Western North Pacific. Okay, so we actually also have a stretch grid version, so that has a spatial region near Taiwan. It's about 9 kilometers. Okay, and by using this stretch version, actually both the number and the strength of the tropical cyclone can be simulated closer to the observations. Okay, so you see some fine resolution does help, especially locally in Western North Pacific. And we use this model, the circular grid, not a stretch grid model, to do a future projection on tropical cyclone activity in Western North Pacific. And it's surprisingly, we see a large reduction in tropical cyclone activity in this area. Okay, so this is the number of tropical cyclones in the future, and this is present time. So a large decrease in the season from August, September, and October. Okay, and this is the sea surface temperature anomaly. We used to force this high rain, and the reason of that is actually the Western North Pacific here become much stable, probably due to the effect of the warm sea surface temperature and also increase of carbon dioxide. And also when the total number is reduced, actually a stronger tropical cyclone typhoon actually enhanced. Okay, so you got more weaker and stronger tropical cyclone in the future in the Western North Pacific. So and that's because it's become much stable and also associated with the enhanced tropical anticyclonic circulation in this area. So that explains that's why it produced a very it simulated result of great reduction in tropical cyclone in these regions. It's very interesting. Not quite sure whether it's going to happen or not, but this one result from this model. Okay, so we also help GFDL to couple the high rain to a step ocean model and also to SIT. It has been completed and been doing testing. And also do some model evaluation and climate diagnostics, model evaluation, simulation, and projection on several aspects, interannual variability and extreme rainfall, summer monsoon, WITCC issues, and heat wave, monsoon, and a lot of things. Okay, and also do some climate diagnostic on extreme rainfall, and also use a model to diagnose the impact of the topography and precision on the monsoon and many things here. I show you some example here. So this work by Xiaochen Liu, Professor Xiaochen Liu. He's probably not here. So he analyzed the data of past almost 40 years. So so they found that how much of the total rainfall will increase by per degree of temperature increasing. Okay, so the increasing increased ratio is actually quite significant. And this work by Chachi Wang. So she tried to understand what happened to this WITCG in CSM 1. It's a serious problem in many models that cannot be solved. Probably each model has its own problem, but for this CSM, they try to understand what happened. So there's a bias within the campfire cell, and they look at this issues, this problem from the perspective of inertial instability and atmosphere-ocean interaction. So they actually found that this bias was actually enhanced after you couple through the atmosphere ocean interaction. So they have submitted a paper to Journal Climate, and they have some explanation. I guess they also have a poster. You can go to see that if you are interested. And our a postdoc from France, Nicolas, he has been analyzing the extreme rainfall in various models. Especially recently, he has been working on the comparison between the semi-fi and high rain, and there's some difference. Okay, so he tried to make sense out of that. Okay, and also he's from Europe, so he's very interested in this ability of high rain to simulate a more detailed structure or rainfall structure in south of France. Got 10 minutes, right? Okay. Okay. So this is some of the diagnostic work related to the model output. And here is a work by Chuhua Wu, and he has been very interested in this effect of topography on Asian summer monsoon. So he submitted a paper to the Journal Climate. I guess that's already accepted or printed, and to see this elongated small island in the Indochina Peninsula does have some great impact on Asian summer monsoon. Okay. And also he revisited this paleoclimate issue problem by increasing this topography in Asia, like Tibetan Plateau, and to look into detail, in much greater detail. Those probably will not paying too much attention to on this different aspect of Asian monsoon rainfall, like a spring rain, like pre-May rain, May rain, and summer rain. And you see that for some particular type of rainfall, the increasing of topography high has significant impact. But for the May rainfall along near the Changjiang, Yangtze River Valley, does not have a significant impact. And another postdoc, Huang-Hsiung, she's continued to use this ACAM5 system to look into this effect of the erosion and the topography, especially in the American continent, their impact on meta-endurance simulation. So there are some comparisons, especially for T213. It produced more realistic simulation compared to T63, so the erosion does help. And she also demonstrated that by removing the topography or by removing the land, it does affect the propagation speed or tendency of the meta-endurance oscillations. It's quite interesting to look into the what sort of dynamics that lead to what kind of mechanism lead to the change in dynamics. Okay. And Jun Chen also used the same system to do a simulation for the on this meta-endurance oscillation characteristic in a warming world, for example, by the end of the 21st century. So you see the enhancement of this meta-endurance oscillation, and also it's become more active in a shorter periods. And it's deeper convection and more moisture conversion near the surface, so everything got enhanced. And okay, that's so much about the core project. Then I will give a brief discussion on the three sub-projects. Because this project will be also introduced in the tomorrow's afternoon, so I'll just give you a brief flavor. So this project called Development of Cloud and Aerosol Parameterizations for Climate Model, led by J.P. Chen with some collaborators from USA and China. And okay, they have been doing a lot of things. So I'll show you probably just 3 or 4 tasks that have been carried out. So they're adding this ice crystal shape parameterization scheme into WRF and essentially probably into the CSM. And they found that by including this new scheme, they got a good performance in simulating the ice crystal number, concentration, box shapes, and the positional heating rates. Okay, so it does do something good to the model. And also they're testing how the aerosol affect typhoon. This one typhoon, a very famous typhoon near Taiwan. So this observation from CCliCS, and they input this natural aerosol and also with the anthropogenetic aerosol. So they found that actually when they increase also on the natural aerosol, they got a better simulation. But after they incorporate the anthropogenetic aerosol, it actually make the typhoon weaker and wider. And so they also input their cloud scheme, detailed cloud scheme to the CSM. And here it shows that after implement that into the model, they improve this. This is an example that's cloud water thickness or optical depth, and I mean the cloud water thickness. Okay, and this observation here, two observations. You're not quite sure about the quantity, but it does show some ITCD, SPCD, but in the CAM file, you cannot find that. Okay. After incorporating his scheme, you start to see some major structures you should observe. And also, they look at this aerosol effect on East Asian summer monsoon. I will go through this quickly. And sub-project 2, working on development of regional climate modeling system by Peter Lin at National Central University. So they are doing some testing to know what sort of spectral margin would have effect on the simulations. And one of the things they have been doing is they try to update the land use type for Taiwan by using more of this data. And they demonstrate that also by including topographic data forcing, and they demonstrate that it can improve the diurnal cycle or more detailed convection structure in Taiwan or the land sea breeze. And recently they updated the soil textures, and they found that significant change to the soil moisture in particular region by using the model with this one. And the last one is done by Chen with a very long title, but essentially the detection and attribution of the anthropogenic effect. Okay, so he took this typhoon Morocco, occurred in 2009 as an example. So he did he defined the so-called anthropogenic effect. Okay, and with and without that. And he did some simulation using a CREST model, Japanese CREST model. And one thing he found is quite interesting, that even using the same regional models, but driven by different reanalysis, you got very different results, especially in precipitation. This observation here, this observation here from TRIM, and this 7 simulation using different reanalysis driving this model. And then you can see my eyes, the precipitation distribution is quite different. It turned out YOTC, European Center YOTC data produce the best data, best simulations. So it tells us you got to be careful when using different reanalysis. Even the track is quite similar, but precipitation can be quite different. So he tried to, estimate how much the so-called anthropogenic effect supposedly that has happened in the future, and how much of that contribute to the large rainfall of the Taiwan Morocco. But to our surprise, actually, he cannot get any answer. But probably not surprised because it's too complicated. And actually, he even showed that by removing the so-called anthropogenic forcing, precipitation in some part of Taiwan Morocco actually got enhanced. Okay, so that's just something to tell us that we cannot attribute all the change to the greenhouse warming effect. Okay, the nature is very complicated. Okay, so that's my presentation. So I hope I did not bore you, and I will entertain some questions if I have time. Thank you.
Thanks, Professor Shi. So due to the time limitation, probably we can have one quick question if there is any. Yes, Professor Yang.
Thank you for the comprehensive overview of the work performed here. I have a question regarding the motivation of doing this new model development. Is for participating in IPCC next round of IPCC, or is just for what other purposes?
Okay, probably it's too late for the CCliCS, but maybe okay if there will be a CCliCS 7. Okay, so what we try to do is we call it a model, a project for capacity building. So because we do not have enough expertise in climate model, but we do some friends from overseas, and we do some talents in Taiwan. So we just taking this project as a vehicle to put people together. So that's why we form a consortium from different, they have a different expertise. So contribute their experience. So we try to, one thing is to try to train good people in not just climate modeling, but in modeling, right? And also, by the end of that, we can have a good tool working on climate change study. Okay, so potentially we probably can contribute to international community. Yeah.
Okay. So that's
thank you.
thanks, Professor Shi again.